Hello and welcome to this session on binary logistic regression. I'm Dr. Sujata Suvarnapathaki, Associate Professor in the Department of Statistics at Ram Narayan Ruya Autonomous College. In this video, I'm going to explain the technique of binary logistic regression with the help of a case study. This session will briefly cover the introduction to predictive models, different types of predictive models, binary logistic regression in particular, that will include the statistical model for binary logistic regression, the model parameter estimation, global testing, individual testing, what is classification table, the ROC curve concept to measure the model performance, and all these aspects will be discussed with the help of statistical programming language R. Let us first learn what are predictive models. Predictive models are the statistical or mathematical equations developed using the historical data or from purposely collected data. Predictive modeling is the process by which a statistical model is created to best predict the outcome or the probability of an outcome. Financial services, insurance sector, telecommunications, retail sector, travel industry, healthcare industry, pharmaceutical industry, sports, etc. are the areas where the predictive models are used. This table lists the different types of predictive models. Binary logistic regression is a non-linear regression model. Apart from binary logistic regression, there are other regression models like ordinal logistic regression, multinomial logistic regression, Poisson regression, Cox regression in the class of non-linear regression models. Whereas time series regression models deal with prediction or forecasting time series data. The difference in the multiple linear regression and binary logistic regression is that the dependent variable is binary in binary logistic regression, meaning the target variable or the outcome variable takes only two possible values, 1 or 0. The independent variables can be continuous or categorical, or it could be a mix of continuous and categorical variables. Binary logistic regression finds its application in the wide range of areas like marketing analytics, where we use cross-sell and upsell modeling, churn management, where we are interested in predicting the customer churn or the employee churn, risk management, where we deal with credit scoring or fraud detection kind of models, and predictive models or this binary logistic regression model in particular may find its application in market research and clinical research. Binary logistic regression modeling can be used in many situations to answer the research questions. We can use it to predict the presence or absence of a characteristic or outcome based on the values of a set of predictor variables. It can help us answer questions like what factors influence the customers to buy certain products, or what are the risk factors for certain disease, or the factors that influence the employees to stay or leave the organization, or the question like what factors influence the customers to default their payments for their policies. This slide explains why multiple linear regression cannot be used in case where y, the dependent variable, is binary. Look at the model equation. If y is binary, then it takes only two possible values, 1 or 0. Whereas the right-hand side is continuous, meaning it can take value between minus infinity to plus infinity. And hence there is a mismatch for the left-hand side and the right-hand side of the equation. If we use P instead of Y on the left-hand side of the model, then the linearity does not hold true. So the shape of the curve is S-shaped curve. So the final statistical model for binary logistic regression is given as seen in this slide. So if y is the binary dependent variable and x1, x2, xk are k independent variables or predictors, then the model for binary logistic regression is given as log of p upon 1 minus p equal to b0 plus b1 x1 plus b2 x2 plus bk xk, where p is the probability that y is equal to 1. So what is the likelihood that y takes value 1? B0, B1, Bk, etc. are called as the parameters of the model, and these parameters are estimated using maximum likelihood estimation method, or it is called as method of MLE. Let us see how this transformation helps to match the two sides of the model. So if y is binary, it takes only two values, 1 or 0, and we cannot use y as it is on the left hand side. Whereas p, which is the probability that y is equal to 1, it will lie between 0 and 1. So p upon 1 minus p lies between 0 to infinity, and hence if we take log of p upon 1 minus p, that term will lie, or that quantity will lie between minus infinity to plus infinity. As a result, we shall achieve the match between the left hand side and the right hand side. Here are a few essential stages in the model construction. First, we understand the data and pre-process the data, meaning in case if there are any missing data points or something, we will be able to take care of those data points. We then perform exploratory analysis. For any statistical analysis that we do, EDA is the first step, which gives us the first cut information about the data. That may include finding summary statistics or doing some graphical representations, data visualization, etc. Then we select the model depending on what data we are trying to analyze. Then we validate the model prior to model implementation. Let us consider a case study in order to understand how we can build a binary logistic regression. This is a case study in banking industry, and the data set that I'm going to use out here is available on kaggle.com. So the data set is about it's about a multi-state bank with the following variables. So customer ID, credit score, country, gender, age, etc. These are all the predictor variables, and churn, which is the target variable. The variable churn takes two values, 1 and 0. So it takes value 1 if the client has left the bank during some period, and it takes value 0 if the person or the customer has not left the bank. The objective here is to predict the customer churn for ABC Bank. This is the snapshot of the data. Let us understand different steps involved in binary logistic regression. First one, build a model wherein we estimate the parameters. Then we test the hypothesis for the significance of independent variables using global testing and individual testing. We then evaluate the model prior to model implementation. Global testing involves testing a null hypothesis that none of the independent variables are significant against the alternative hypothesis at least one variable is significant. When we perform this global testing using R, we get a p-value, and the decision criterion is reject the null hypothesis if p-value is less than 0.05, which is the level of significance. Similarly, we test k pairs of hypotheses for testing the significance of each of the k predictors. The decision criterion is reject the null hypothesis if p-value is less than 0.05, which is the level of significance. Let us see how to carry out binary logistic regression using R. Firstly, we import the data file in our environment. So this data is in the CSV format. So we import this data using read.csv file.choose command. We observe the first 6 rows of the data using head function. The categorical variables are to be treated as the factor variables in case if they are numbers like 1 or 0 or 1, 2, 3. Meaning if the categorical variables include numerical data like say for example gender. If the gender variable is written as either 1 or 0, meaning 1 indicating male or female and 0 indicating female, then this variable cannot be used as it is unless we treat that as a factor variable. This is the output of the head function. Now, as you see in this slide, the credit card active member, they are 1 or 0. So credit card 1 or 0 indicates whether the person is holding a credit card, then it is 1. If he or she doesn't hold a credit card, it is 0. So this variable needs to be treated as a factor variable, and so also the variable active member. So active member variable takes value 1 if the member is active, and if the member is inactive, it takes value 0. So again, this variable needs to be treated as a factor variable. Let us see how to build binary logistic regression using R. So to build binary logistic regression, the GLM function is used. GLM stands for the generalized linear models. We include the arguments like specifying the model, and then we use summary function that displays the detailed output of the model. Here is the output. We can see that the parameter estimates and also the results of individual testing being displayed as the output of summary function. So the first column of estimates indicates the model parameter estimates, which is done using method of MLE, and the last column here, which is of p-values, indicates which independent variables are significant and which are not. This is how we interpret the output. The independent variables, namely the credit score, the category of the variable country, which is Germany, with respect to the base category France, the category of the variable gender, which is male, with respect to the base category female, age, balance, product numbers, the active member category 1 with reference to the base category 0, these are all significant variables since the results of the individual testing say that the p-values are less than 0.05. For the model implementation, we need to retain only the significant variables, and hence we rerun the model by keeping only the significant variables. The churn model 1 is now the new object that we are defining, wherein we again specify the GLM function, wherein we retain only the significant variables and the rest of the arguments as they are. Summary of this new object, churn model 1, is then checked. These are the results of the model with only the significant variables. So basically, this is the output for the revised model. The next step is model application. We apply the built model to the data. This is done by fitting the model by which the predicted probabilities are calculated for each case in the data, and they are also appended in the original data. The cutoff for the predicted probabilities needs to be decided. Using these predicted probabilities and the cutoffs, the classification of each case as either 1 or 0 can be done. So we have the observed values of the dependent variable y and also the estimated values of y based on the cutoff for the predicted probabilities. Using the observed and the estimated y, we can get the classification table. The classification table enables us to measure the goodness of the model. Let us see how to fit the model to the data using R. The first line on this slide indicates the syntax for appending a column pred prob into my original data bank churn using fitted function. Fitted churn model 1 will apply the final model to the data, and round function will allow us to round off the predicted probabilities up to 4 decimal places. Let us see how to obtain classification table using R. To obtain the classification table, we install the package gmodels. Then use the library gmodels. The function cross table applied on the target variable churn and the predicted probabilities using the cutoff 0.2037 in this case. Now this cutoff 0.2037 is obtained as the proportion of ones which are present under the target variable churn in the original data. Classification table measures the goodness of the model. This is the output of classification table which we have obtained using the cross table function. In rows, we have the observed values of the dependent variable y, and in the columns, we see false indicates y being classified as 0 and true indicates y being classified as 1. The first number in each cell of this classification table indicates the frequency of classification, whether it is correct classification or misclassification. Let us see how to find out the misclassification rate. The misclassification rate indicates the percentage of incorrectly predicted observation, which is contingent on the chosen prediction cutoff. Now, in this case, the misclassification rate is calculated as 2338 plus 628 out of 10,000 observations, resulting in a rate of 29.66%. So if you apply the model, there is a 30% chance that the model will incorrectly predict the customer to be a churn or a non-churn. Let us now understand the terminology related to classification table. We deal with 4 major terms here like sensitivity, specificity, false positive rate, and false negative rate. Sensitivity is defined as percentage of occurrences correctly predicted. Specificity is defined as percentage of non-occurrences correctly predicted. False positive rate is actually complement of specificity, and false negative rate is the complement of sensitivity. Sensitivity and specificity values change as per the cutoff. Cutoff can be determined by trial and error method. At times, the domain knowledge helps in deciding the value of cutoff. This cutoff is to be applied on the predicted probabilities. So most of the times, the cutoff is considered to be the proportion of occurrences in the data being analyzed. And what we understand by occurrences is nothing but y being equal to 1. Cutoff is helpful for actual classification of the cases from the out of sample data. A better method to measure the model performance though is to plot the ROC curve or the receiver operating characteristic curve and also the area under the ROC curve. Let us see how to judge the model performance using ROC curve. The ROC curve is a graphical representation commonly used to evaluate the performance of binary classifiers using binary logistic regression models. It presents a clear view of the trade-off between the true positive rate, that is nothing but sensitivity, and false positive rate, which is 1 minus specificity at various classification thresholds. So to construct the ROC curve, we follow the steps like train the binary logistic regression model using labeled data to predict the probability of instances belonging to the positive cases, that is class 1. Obtain predicted probabilities for a separate validation or test data set. Set different classification thresholds to convert probabilities into binary predictions, and that would happen automatically in R. Calculate the true positive rate and the false positive rate for each threshold Plot TPR, that is the true positive rate or sensitivity, against the false positive rate, which is 1 minus specificity, to create the ROC curve. The area under the ROC curve is a metric which quantifies the overall performance of the classifier, with higher values indicating better performance. A perfect classifier would have an ROC curve reaching the upper left corner, meaning TPR is equal to 1, FPR is equal to 0, representing 100% sensitivity and 0% false positive rate, which is basically a rare situation, while a random classifier would follow the diagonal connecting the points 0, 0 and 1, 1. In conclusion, the ROC curve is a valuable tool to visualize and assess the effectiveness of binary classifiers, enabling the selection of an appropriate classification threshold based on the desired balance between sensitivity and specificity for a specific application. Let us see how to get ROC curve using R and also to find out the area under the ROC curve. So we have to install a package ROCR and call for the library ROCR. Using the subsequent steps, we will be able to find out the ROC curve as well as area under ROC curve. So here are the steps, or this is the R code to obtain the ROC curve and area under ROC curve. This is the output. So as you can see, area under ROC curve is 0.7670. So let us see what's the conclusion of the predictive modeling exercise for our data, which was for ABC Bank, and the objective was to predict the customer churn. Since the area under the ROC curve is 0.7670, this can be treated to be a fairly good model, and hence the model can be implemented to predict the customers who are likely to churn. But it is advisable to also perform cross-validation before implementing the model. Cross-validation is a process of evaluating the model for out-of-sample data. The model performance measures for binary logistic regression, such as accuracy rate, sensitivity, specificity, tend to be optimistic on in-sample data. More realistic measures of the model performance are calculated using the out-of-sample data. So cross-validation is a procedure for estimating the generalization performance in this context. Cross-validation is important because although a model is built on historical data, ultimately it is to be used for the future data. However good the model, if it fails to predict for the out-of-sample data, then it defeats the purpose of predictive modeling. So in our case, though we are almost ready for implementation, it could be a good practice to perform cross-validation on our data. Let us see how to perform cross-validation in short. Holdout validation is one of the sought-after cross-validation method. And of course, there are several other methods like k-fold cross-validation, repeated k-fold cross-validation, or leave one out cross-validation method. Let us see how to perform holdout validation. In this kind of validation method, we divide the original data into two non-overlapping subsets, wherein we reserve either 70 or 80% of the data as training data and remaining 30% or 20% of the data as the test data. The model is developed using the training data and it is evaluated using the test data. So what we do is we get ROC curve and area under ROC curves evaluated for both training data and test data. And if ROC curves look more or less similar and the area under the ROC curve values are similar, then we can confirm that the model is good enough. Here are some important points that one needs to remember. Predictive models rely on the historical data and are influenced by two crucial factors, which is sample size, and data dimensionality, which is the number of variables. When the sample size is too small, the model may not be representative of the entire population, resulting in poor performance and unreliable predictions. Limited data can introduce bias and lead to unexpected outcomes. Similarly, when dealing with a large number of variables but a limited number of observations, the model struggles to identify meaningful patterns, leading to instability in the results. Learning from such small sample can be problematic and hinder the model's accuracy. To secure a stable and dependent predictive model, a general guideline is to aim for an observation count which is 8 to 10 times the number of variables. For example, if there are 10 variables in the study, a stable model would require at least 80 observations. So these are the important tips which are to be accounted for when you are doing any predictive modeling exercise. Well, with this, we have come to the end of our discussion on binary logistic regression, and I would like to thank you for your time and attention. I would also request you to write your comments if you have any questions in the comments section, and I would surely come back to you with the answers. In addition to this, I have also uploaded the notes on binary logistic regression, as well as there is a short quiz that you can take on binary logistic regression. I would once again thank you for your time and attention. Thank you again.